divided into two sections. The first section introduces the gate driver, and the second section covers isolation solutions. Firstly, what is gate driver? Gate driver is a buffer circuit between the low-voltage controller and high-power circuit, which is used to amplify the control signals of the controller for more effective turn-on and turn-off of power devices. The functions of gate driver are as follows. Firstly, gate driver can convert low-voltage signals from the controller to high-voltage signals to drive power devices. Secondly, gate driver can provide transient source and sink peak currents, which can improve the switching speed of power devices and reduce the switching loss. Thirdly, gate driver can effectively block the noise of high-power circuits, keeping the system stable. Fourthly, gate driver integrates protection functions to protect power devices from getting damaged. In conclusion, gate driver is used to ensure better performance of power devices in the system. There are four types of common power devices. Silicon MOSFET devices, which withstand voltage of 20 volts to 650 volts and are suitable for low-power systems. Silicon IGBT devices, which withstand voltage of greater than 650 volts and provide a strong current endurance capability. This type is suitable for high voltage and high power systems. Both of them are silicon-based power devices that have been widely used. Silicon carbide MOSFET devices, which provide withstand voltage range comparable to IGBT, but feature fast switching speed and low switching loss, more suitable for high voltage and high power systems. GaN devices have a withstand voltage of less than 650 volts, but provide obviously advantageous switching performance, suitable for high-frequency and high-power systems. Silicon carbide MOSFET and GaN devices are third-generation wide bandgap semiconductors, offering significant performance advantages over traditional silicon-based devices. Each type of power device requires specific gate driver solutions. Currently, NOVOSENSE has developed driver products suitable for these four types of power devices. How does a gate driver control the turn-on and turn-off of power devices? Below is a detailed explanation of the switching process of power devices. In power devices, there are equivalent parasitic capacitances. The switching process of a power device can be equivalent to the charging and discharging process of its parasitic capacitances. In the turn-on process, the driver IC connects the output signal to the driver power supply through an internal source, current MOS, and charges CGS and discharges CGD through a gate resistor. T0 to T1 stage. The gate current charges CGS and VGS gradually increases. At this point, the power device is still turned off. T1 to T2 stage. When VGS increases to a value greater than the gate threshold voltage, VTH, the power device begins to turn on, and IDS increases with VGS until it reaches its peak. T2 to T3 stage. This is the Miller plateau period, where the gate current mainly discharges CGD and VDS begins to decrease. The device is fully turned on. T3 to T4 stage. The gate current continues to charge CGS, and VGS gradually increases to the power supply voltage. When the gate current reduces to zero and turn-on process ends, the turn-on loss of the power device mainly occurs at the T1 to T3 stage. In the turn-off process, the driver IC connects the output signal to the GND through an internal sink current MOS and discharges CGS and charges CGD through a gate resistor. T0 to T1 stage. The gate current mainly discharges CGS and VGS gradually decreases. T1 to T2 stage. This is the Miller plateau period, where the gate current mainly charges CGD and VDS begins to increase. When the voltage reaches VDC, the Miller plateau ends. T2 to T3 stage. IDS begins to decrease. When VGS decreases to VTH, IDS drops to zero, and the power device is completely turned off. T3 to T4 stage. The gate current continues to discharge CGS, and VGS eventually drops to zero. The turn-off process ends. The turn-off loss of the power device mainly occurs at the T1 to T3 stage. It can be seen that shortening the T1 to T3 stage can effectively reduce the switching loss of power devices. At present, there are three typical gate driver ICs. namely non-isolated low-side drivers, non-isolated half-bridge drivers, and isolated drivers. Non-isolated low-side drivers are only suitable for power devices with reference to GND and provide dual-channel or single-channel driving capability. Non-isolated drivers are relatively simple to implement, requiring only single power supply. They are mainly used in low-voltage systems. Currently, NOVOSENSE offers non-isolated low-side driver ICs including NSD1026V and NSD1015. Non-isolated half-bridge drivers are used in power systems with a half-bridge configuration. The withstand voltage of the high and low sides is usually achieved through level shifting or isolation, ranging from 200 volts to 600 volts. To prevent shoot-through, half-bridge drivers provide an interlocked function. When a non-isolated half-bridge driver is used in the system, single power supply plus bootstrap power is typically adopted. This driver IC type is mainly used in low-voltage or high-voltage systems. Currently, the half-bridge driver ICs from NOVOSENSE include NSD1624 and NSD1224. Isolated drivers use an internal isolation barrier to physically isolate high and low voltages. Isolated drivers provide flexibility in application. Single-channel and dual-channel isolated drivers are available for low-side, high-side, or half-bridge applications to achieve primary and secondary isolation in the system. The high-voltage side requires an isolated power supply, making the power supply system relatively complex. Isolated drivers are mainly used in high-voltage systems. Currently, NOVOSENSE offers multiple isolated driver ICs including dual-channel, single-channel, opto-compatible, and smart isolated driver ICs. In a high-voltage power system, there is usually isolation between high voltage and high voltage, as well as between high voltage and low voltage. First, an isolated driver can protect people from high voltage and meet safety standards through isolation. Second, it can shield the control system from lightning and sudden high voltage. Third, an isolation driver can remove ground loops and cut down interference between high and low voltage areas. Fourth, it can convert voltage or current and transfer energy. There are three typical isolation solutions. The first one is optocoupler isolation, which achieves signal transmission through light-emitting diodes and phototransistors. It is low cost but provides lower CMTI, limited temperature range, and short lifetime. The second one is magnetic isolation, where the chip integrates micro-transformer and electronic circuit to achieve signal transmission. It provides a long lifetime, wide temperature range, and higher CMTI, but involve complex technology, high cost, and prominent EMI issue. The third one is capacitive isolation, which achieves signal transmission through isolation capacitors and electronic circuits. It usually uses silicon dioxide as the insulating material. The capacitive isolation solution features low cost, long isolation life, wide temperature range, and strong CMTI. NOVOSENSE adopts the capacitive isolation solution. Isolated driver ICs from NOVOSENSE usually have two dies. The primary die is on the input side and the secondary die is on the output side. There is a physical isolation between the dies. Two isolation capacitors are connected in series on the die to provide double insulation capability. If one of the dies experiences an EOS failure, the driver IC can still maintain basic insulation capability. The top and bottom substrates of the two isolation capacitors are insulated using silicon dioxide, which can ensure stable material properties, good chip consistency, and long isolation life. The top substrates of the two isolation capacitors are connected by metal wires for signal transmission. NOVOSENSE's isolated driver ICs can withstand surge voltage up to 12 kV and 8 kV transient voltage, far exceeding the insulation requirements of high-voltage systems. The communication between the dies adopts the differential OOK modulation scheme, which ensures stable and reliable communication. The input signal is modulated at high frequency and then transmitted from the primary die to the high-voltage die through the isolation capacitor, with the modulation frequency at a level of over 100 MHz. A proprietary CMTI modular circuit is added at the input side of the differential signal, allowing the IC to achieve a stronger CMTI capability up to 150 volts per nanosecond. For power systems with a high dV/dt, the IC can still work stably without abnormal wave emission. NOVOSENSE provides a wide range of gate driver products. For sample requests or orders, you can send an email to us. More information is available on our official website.